So today we're looking at differential equations, where a differential equation is an equation that's got a function mixed in with one of its derivatives. So what we're looking at today is how we can find the original function without its derivative in there, or how to reverse this sort of thing. So looking at this, do we have any ideas of how we might do it? Yeah, probably integrate. So if you've got a dy over dx, and then it's equal to 2xy, then what we're going to find is that we can get this sort of equation here, and we can rearrange it in terms of y is on the left, x is on the right. So in this case, what we're going to do is, it's going to turn into dy over y. Then on the right-hand side, it's 2x dot dx. Dot meaning time. So all we've done is we've divided both sides of the equation by y, and then multiplied both sides by x. From there, we can simply integrate, like so. The integral of this, this is a 1 over y with respect to dy. Integrating that, it turned into an ln y. And then on the right hand side over here, we're integrating 2x with respect to x. That's going to give us, it's going to give us x squared. And then we've got a plus c for the constant. From there, we want to find this in terms of y, so we simply raise both sides of the equation to the power or to a base of e. So this is going to be e to the ln y, which is just y. So it becomes e to the x squared. And even though it should be e to the c, we just say c. And the reason for that is because c is an arbitrary constant of integration. So what we've done in this instance over here is we've got a differential equation and we've rearranged it back into its, let's say, an equation that's not a differential equation, just by moving all the functions of y to the left and the functions of x to the right, and then just integrate both sides. So this is, okay, so this over here, we call this a general solution. To, in this case, it's dy over dx, 2xy. Seem cool? All right, that's pretty straightforward, nothing that we haven't seen before. But what happens if we're quite particular about what it is we're trying to find? Example, find y given, and we will say, from my example, that will go find y given this, where we'll say y x equals 2 is equal to 20. Do you understand that notation?
What?
So when x equals 2 to the value of y, you're going to get 20.
Right.
Let's not do that. Y of 2 equals 20. Does that make sense?
Yep.
So y is a function of x.
Oh, so we're using that to find c.
Yep.
Okay.
So looking at this one, what would we do to try and solve this? Starting with this guy up here. dy over dx is 4x cubed. What's the first thing we need to do to be able to solve this differential equation?
Rearrange.
We need to rearrange it by separating the y's and the x's. Y's go to the left, x's go to the right. Or you can do it the other way around, it doesn't matter. So to do this, we times both sides by dx, and we divide both sides. No, we don't divide both sides. We just times both sides by dx. This will give us the effect. dy is 4x cubed dot dx. Next step, which we can show on the same line, what are we going to do? We don't want the change in y and the change in x, we just want x and y. So we integrate. There's nothing between the integral symbol and the dy, so that just becomes a 1. Dot. Next, left-hand side becomes y. Right-hand side becomes 4 over 4x to the 4 plus c. Therefore, our general solution is y equals x to the 4 plus c. So this is our general solution. But we can do better in solving this, can't we? Because we know something particular about this equation over here, don't we?
Yes.
What do we know about the equation, Leishman?
When x equals 2, y equals 20.
But y of x equals 2 equals 20. So what this infers is that we can go 20 equals 2 to the 4 plus c. c is going to be 20, take 2 to the 4. 2 to the 4 is 16, is it not? So c equals 4. Therefore, let's see, y equals x to the 4 plus 4. And what we call this over here is our specific solution. It's specific to a specific case, in which case in the reality where when x equals 2, y equals 4, that's the solution we get. You're going to find that because we lose information when we differentiate, so we lose that constant term, the information's lost, so your equation's different when you try and reverse it. So if you try and reverse it, you need to have a particular point. Any questions?
Nope.
That's about as hard as it gets today. There's a question in here that's an integration by parts. I thought it was quite fun. So, yeah, quite the delight you've got in front of you.
Oh yeah.
But it's honestly, that's as hard as it gets. The idea is if we're trying to solve differential equations, separate the variables. So y is on the left, x is on the right. Integrate if you're going for a specific case, then after you finish the integration part, you go down into finding the specific solution. First chapter that I've got listed for you, it's just general solutions. Second chapter, you're looking at specific solutions. Not much to it that you already haven't seen. All good?
Sweet as.